a particular example with two processes, process 1 and process 2, and we will represent the state of the system by this particular graph. Now, on the x axis are the instructions executed by process 1, and the y axis corresponds to the instructions executed by process 2 with respect to time. So, both are with respect to time. Thus, process 1 and process 2 begin to execute from the origin, that is this point over here, and they complete execution at the other end, that is the point over here. Now, as these process executes in the system, the state of the system will change, and the state changes depending on how these two processes execute with respect to each other. So, let us say this state is represented by each of these blocks over here. Now, this line over here indicates the execution path. For example, over here the line is horizontal, indicating that instructions corresponding to process 1 gets executed. So, as a result of process 1 executing while process 2 not executing, we get a state of the system over here, which is shown by this small square. Then the state is shifted to this as shown over here, and then at this particular point there is a context switch and process 2 executes. So, as a result of process 2 being executed, the state of the system gets shifted to this point. Then process 1 executes again and the state changes, then process 2 gets executed, process 1 and so on, and at the end we will have both process 1 as well as process 2 reaching this particular point. Essentially both processes have completed execution. Now, you see, depending on how the operating system schedules, how various resources are allocated or deallocated to process 1 and process 2, this particular trace, or rather the execution trace of the process 1 with respect to process 2 would vary. For example, in the worst case it could be like process 1 executes continuously till it completes, and then process 2 executes completely till it completes. Or another technique would be like process 1 executes a few instructions, then process 2 executes a few instructions, then process 1, process 2, process 1 and so on till both of them complete. Now, let us also state that process 1 and process 2 requires a resource R1 during its execution. So, process 1 requires the resource R1 at this particular time. So, this particular time over here, which is shown at this point. So, these instructions in process 1 requires the use of resource R1. So, this has been highlighted by this purple block over here. Now, in a similar way, during this time from this point to this point, process 2 requires the use of resource 1. So, this has been highlighted over here. Now, this intersecting square is the region where both process 1 as well as process 2 require resource 1. So, this intersecting square represented by the intersection of these two regions correspond to the instructions in both processes that request resource R1. Similarly, let us say that there is an other resource R2 which is required in these particular instructions by process 2 and these particular instructions in process 1, and we correspondingly obtained a intersecting square as shown here, and this square represents the part where both processes P1 and P2 request resource R2. Now, what we will see is the intersecting part of R1 and R2 resources. So, if we actually intersect this graph with this graph, we get the points where both processes request R1, that is this purple part here, and this part is where the both processes require R2, and the intersecting area is where both processes require both resources R1 and R2. Now, this area is which may potentially cause a deadlock. So, we call this as an unsafe state. So, an unsafe state is not a deadlock state, but rather it is a state which may potentially cause a deadlock. Thus, if the OS was to schedule the process 1 and process 2 in such a way that the execution path ends up in this unsafe state, then we may potentially have a deadlock. On the other hand, if the OS schedules process 1 and process 2 execution in such a way that this unsafe state is avoided, then the deadlock is avoided. So, this is the essential technique used to avoid deadlocks in systems. So, the next question is there an algorithm that can always avoid deadlocks by conservatively making the right choice? That is, can we ensure that the system never reaches an unsafe state by making some choices in the way processes execute or the way resources are allocated and so on. So, one way that we can build such an algorithm is by using what is known as a banker's algorithm. So, let us see an example with this. Now, consider a banker with 3 clients A, B and C. Each client has certain credit limits, and the sum of all these credit limits totals to 20 units. Now, the banker knows that the maximum credits of 20 units will not be used all at once. So, he keeps only 10 units. To see what this means, let us say we consider this table with the 3 clients A, B and C, and each client has in his account some units. So, for instance, A has got 3 units, B has got 2 units and C has got 2 units. So, is a total of 4, 5, 6, 7, and since the banker only keeps 10 units, so the remaining 3 units are free and not allocated to any of the clients. On the other hand, the maximum credits for each client is 9, 4 and 7 respectively. So, you note that 9 plus 4 plus 7 is the maximum credit limits, which totals to 20 units, and this maximum credit limits is declared by the client in advance. Now, given this particular table, the banker should be able to allocate the maximum credits to users in such a way that no unsafe state is reached. So, let us see this with examples. So, the problem we are trying to solve here is whether these allocations maximum of 9, 4 and 7 can be made to A, B and C in such a way that the state is safe, or rather such an allocation can be made. So, let us say we start with 2 units being allocated to B. So, we have 3 units in the free store. Out of these 3 units, 2 are allocated to B, therefore, B has now 2 plus 2, that is 4 units, and the free store now has 3 minus 2, that is 1 unit free. Now, after B completes, all the 4 units are returned to the free store. So, 4 plus 1 will be 5 units present in the free store, and these 5 units can then be allocated to C. So, C will get its maximum credit limit of 5 plus 2, that is 7 units as seen over here. So, the amount present in the free store is 0 units. Now, after C completes, all the 7 units of C get returned back to the free store. Now, the banker could allocate the resources required by A, that is the maximum resources required by A, that is of 7 more units, to get its maximum credit limit of 9 units. So, we have 9 credit units allocated to A and 1 unit which is free. Thus, we see with this particular start point or this particular state of the system, where there are 3 units free and there is maximum of 9, 4 and 7 units as the credit limit of each client can have. We see that with this particular state, there is a schedule which is possible, so that all requests and all maximum requests by the clients can be fulfilled. So, we call such a state as a safe state, and the banker could go ahead and make such allocations. Now, let us look at another example where the state we start with is that A has 4 units with it, B has 2 and C has 2. So, a total of 8 units are present with A, B and C respectively, and the number of free units is 2, and the maximum credit limits of each client is as before 9, 4 and 7 respectively. Now, we see that irrespective of how the banker tries to allocate these remaining units to each of its clients, there is no schedule which is feasible that could fulfill these requirements. For example, suppose B were allocated 2 more units, and you see that given that there are only 2 units free. So, B is the only client which can be serviced. Therefore, B gets 4 units while there are 0 free units present. Now, after B completes, we have 4 units free, but you see that neither A, which requires 5 more units, nor C, which requires 5 more units as well, can be serviced with 4 units, which is present in the free store. Therefore, we see that this state is an unsafe state, because there is no scheduling order which can cater to these requirements. So, this is an unsafe state, and the banker should ensure that such a state is not reached at any point. So, a similar mechanism can be also implemented in the operating system, where corresponding to each request, the operating system will determine if the system is in a safe state, and if indeed the system is in a safe state, indicating that there is a schedule of the resources, so that all requests can be granted, then the requests are allocated. Otherwise, the request is postponed until later.